Part 2 of Unit 10 is about rate laws. Rate laws are equations that we can derive to calculate the rate of a reaction if we're only given the concentration of the reactants. So this is where we start getting into some interesting math. The general form of a rate law equation is that rate is equal to lowercase k times a and b in brackets raised to the x and y power. Now that lowercase k, that's called the rate constant. That's something we have to solve for. A and b, that's just the identity or the chemical formula of the reactants. The brackets around them mean concentration of the reactants in molarity. And x and y, those exponents are called reaction orders for each reactant. Before we can solve for the rate constant, we have to figure out what the values of the reaction orders are, and we have to do that by looking at a set of experimental data. So looking at this equation, we've got 6 sets of experimental data where we had differing initial concentrations of the two reactants and the different observed rates of those reactions with those concentrations. So to solve for the reactant orders, we've got to do 2 sets of calculations, one for each reactant. And step 1 is we need to find 2 experiments where the concentration of one reactant changes and the other is constant. So if we look at experiments 1 and 2, the ammonium concentration doubles, so it changes. The NO2 concentration stays the same, and the rate changes. So we can use experiments 1 and 2 to solve for the reactant order for ammonium. To solve for the order for the nitrite ion, NO2, we could use experiments 5 and 6 because the ammonium concentration stayed the same, but the nitrite concentration changed. So to solve for the order for each reactant, we need to compare the ratio of rate laws for each experiment. So first we'll do that for the ammonium, NH4, and we're going to compare experiments 1 and 2. So our general form, again, for the rate law, rate is equal to the rate constant times the ammonium concentration to the x times the nitrite concentration to the y. Now what we'll do is take data from experiments 1 and 2 and plug them into the rate law. So we'll take the concentrations from the table on the previous page and plug them in here, and the rate, plug it in here, and we'll do a ratio of those to try and solve for the exponent. When you are doing this ratio, it's easiest to put the experiment that had the larger rate value on top so that you end up with numbers greater than 1. So what we'll do is we'll compare experiments 2 on top and then 1 on bottom. So the rate for experiment 2 was 10.8 times 10 to the negative 7th. That's equal to the rate constant times my concentration of ammonium, which was 0.02, to the x, times the nitrite concentration, which was 0.2, to the y, and we'll put all of this over experiment 1. In experiment 1, the rate was 5.4 times 10 to the negative 7th. It's equal to our rate constant that has to be solved for. The concentration of ammonium was 0.01 to the x, and the concentration of nitrite, since we kept it the same, 0.2 to the y. Now ultimately our goal is to solve for x here. So if we look at this like a division problem or fraction, we can cancel out the rate constant because it's in the numerator and denominator, and we can actually cancel out this entire term of 0.2 to the y because it's in both as well. So to simplify this, we'll just divide 10.8 times 10 to the negative 7th divided by 5.4 times 10 to the negative 7th. So we're going to end up with 2 is equal to, we'll simplify this into one term. 0.02 divided by 0.01 is 2. We'll leave our x. So now all we have to do is solve for x. Well, 2 to what power equals 2? X has to equal 1. So we would go back up here to the rate law and change this x to a 1. That means that ammonium is a first order reactant. X can be 0, 1, 2, or 3. It can really be any number, but what you'll commonly see is 0, 1, 2, or 3. Now, if we did the same process with experiments 5 and 6, we would actually end up with the same value of the rate order for nitrites. So they would both be first order reactants. The overall rate for this reaction would be second. We just add the order for each reactant together. So let's look at another example. We need to write the rate law for the following data and determine the value of the rate constant. This time I'll show you how to find the order for both reactants. Now, if you remember in that first equation, both reactants ended up being first order, and they both had a coefficient of 1. That's coincidence. We can't ever assume that that is going to happen. You have to determine the order for each reactant experimentally. So in this case, we can't just assume that NO is going to be second order and Cl2 is going to be first order. We have to show our ratio of the rate laws and do the work to solve for the order to be sure. On the AP test, you have to show your work of solving the rate laws for the order to get any credit. So in this example, to find the order for NO, we're going to use experiments 1 and 2 because it changes and Cl2 is the same. And to find the order for Cl2, we're going to use 1 and 3 because NO stays the same but Cl2 changes. So we'll put our general form of the rate law up here. Rate is equal to the rate constant times the concentration of NO to the x times the concentration of Cl2 to the y. We'll first solve for the order for the NO using experiments 1 and 2. But since 2 had the larger value for the rate, I'm going to put it on top. So it's going to be 2 over 1 here. So we'll plug the data from experiment 2 into the general form of the rate law. 5.72 times 10 to the negative 6th is equal to the rate constant times the concentration of NO, and that one was 0.5 to the x, and the concentration of Cl2 was 0.25 to the y. I didn't do a very good job of keeping that one straight. And we'll put experiment 1's data on the bottom. The rate was 1.43 times 10 to the negative 6th, our rate constant. In this one, the concentration for NO was 0.25 to the x, and the concentration of Cl2 was 0.25 to the y. Now again, we can cancel out the rate constant, we can cancel out the Cl2 term. Now we need to simplify things. So if we divide 5.72 times 10 to the negative 6 divided by 1.43 times 10 to the negative 6, we'll end up with 4. And that's going to be equal to, we'll simplify this, 0.5 divided by 0.25 is 2 to the x. Well, 2 to the something has to equal 4, x has to equal 2. So NO2 is a second order reactant. Now let's use experiments 1 and 3 to solve for the order for the Cl2. Again, we're going to put the larger rate on top, so we'll do 3 over 1. Data for experiment 3 is 2.86 times 10 to the negative 6th is equal to the rate constant times 0.25 for our NO2 concentration go ahead and plug the order in there, times the Cl2 concentration of 0.5 to the y. Whoops. Oh well. And then we'll plug in experiment 1's data on the bottom, 1.43 times 10 to the -6th is equal to K times 0.25 to the second times 0.25 to the y. So in this case, we're canceling out the first reactant. We'll get rid of the rate constant and this 0.25 squared. We simplify this, we're going to get 2 is equal to 0.5 divided by 0.25 is 2 to the y. So y is going to equal 1. That means that Cl2 is a first order reactant. So this is our solved form of the rate law. We can then go back and choose any experiment's data to plug in and solve for the rate constant. So once we've determined the order for each reactant, we can solve for the rate constant by choosing a set of data and plugging it in and solving for K, the rate constant. So our rate law was rate is equal to the rate constant times the NO concentration in its second order times the Cl2 concentration in that's first order. So I'm just going to take the data from experiment 1 and plug it into this general form of the rate law. So a rate of 1.43 times 10 to the -6th molarity per second is equal to K times the NO concentration of 0.5 molar squared times the Cl2 concentration of 0.25 molar to the first. It's very important that you put units on all of your values that you plug in here, because the units of the rate constant are a separate point themselves on the AP test because they get kind of complicated. So what we have to do to simplify the right side of this, we'll have to remember to square both the 0.5 and the unit. So we'll end up with 0.5 squared and molarity squared there times the 0.25 times 1 molarity. So to simplify that, we get K times 0.0625 molarity cubed equal to our rate over here, 1.43 times 10 to the -6th molarity per second. Molarity per second. So to solve for K, we need to divide over here by 0.0625 molarity cubed. Now when we do this, this molarity is going to cancel out, so is one of these. It's being divided out. And when we've got a unit like this seconds up here that's in the denominator, but it's being divided by something, we're going to move it down here. So we're going to do 1.43 times 10 to the -6th divided by 0.0625. So our rate constant is going to be 2.3 times 10 to the -5th. And our units, well, we took everything out of the numerator over here, so our units are going to be 1 over molarity squared times seconds. So like I said, you need to be very careful with your math when you're solving for the units for the rate constant. Your question for this section, using the steps illustrated in this video, determine the value of the rate constant including units. That means you have to write the rate law, determine the orders for each reactant, and then go back and solve for K, the rate constant.